I want you to start by picturing a map, but not a map of a city or a coastline or anything like that. I want
Okay.
you to picture the blueprint of a massive industrial complex. Maybe a refinery in Alberta or a chemical plant down in Texas.
I'm with you.
If you zoom in on that map, you don't just see buildings, you see veins.
Hmm.
Miles and miles of steel piping just weaving in and out, stacked up like some chaotic highway system.
It is effectively a circulatory system,
Hmm.
just made of carbon steel instead of arteries.
Exactly. And inside those veins, you've got high-pressure steam, volatile hydrocarbons, acids, stuff that is moving fast under immense pressure and is often incredibly dangerous.
Right.
We know that to control that flow, to stop it, start it, or throttle it, you need valves. But here's the thing I never really thought about until we dug into these NAII seat and S8 training modules.
What's that?
Who or what is actually turning those valves?
Because in a modern plant, it is almost never a guy named Steve running around with a pipe wrench.
Right. You can't have a human standing at every junction of a 10-mile pipe network just ready to turn a wheel the second the temperature spikes. So the industry uses actuators.
The muscle behind the machine.
That is the perfect definition. If the control system is the brain deciding what needs to happen, the actuator is the bicep that actually does the heavy lifting.
Yeah.
Today, we are doing a deep dive into that muscle. We're going to look at the physics of how they generate massive force, the fail-safe logic that keeps plants from, blowing up when the power cuts out, and honestly, the terrifying safety hazards involved in fixing them.
And we are definitely going to get into the bench set.
The bench set, I was reading through the notes on that, and it felt like I was reading a guide on how to defuse a bomb while doing calculus.
It's not far off.
Mm-hmm.
That is where the rubber meets the road, or I guess where the air meets the spring. It's the calibration process that ensures the valve actually listens to the computer, despite all the chaos happening inside the pipe.
So let's start with the basics. The source material highlights three main ways these actuators get their power.
Pneumatic, electric, and hydraulic.
Right, but it makes it pretty clear that pneumatic using compressed air is the absolute king of the hill. Why is air so dominant?
Well, it comes down to two things, really, safety and give.
Okay, let's start with safety.
First, safety. In a refinery, you have explosive gases everywhere. If you have a spark, you have a disaster.
And electricity creates sparks.
Exactly. Air doesn't. If a pneumatic line leaks, you just get a hiss of air. It's annoying, but it's not a fire starter.
That makes a lot of sense. It's inherently explosion-proof.
It is. But the second point is reliability and simplicity. Pneumatic actuators are incredibly robust. They're essentially just a container that expands when you blow air into it.
And the source breaks them down into two families, right?
Diaphragm and piston.
Let's visualize the diaphragm first. The text describes it as having a flexible membrane.
You think of a metal canister sitting on top of a valve. Inside, you've got a sheet of rubber, or neoprene, that's a diaphragm. It seals the canister, basically cutting it in half.
Okay.
When you pump compressed air into the top half, it pushes that rubber sheet down.
And since the rubber is connected to a metal plate and a stem?
The stem goes down, and the valve operates. It's like a low-friction, high-sensitivity lung. It just breathes in air and pushes the valve.
But the text mentions a limitation. It says diaphragms are generally for short strokes.
Right. Rubber can only stretch so much before it tears or loses efficiency. If you need to move a valve stem 6 inches, or a foot like on a massive gate valve, you just can't use a diaphragm.
So that's when you need a piston.
That's when you need a piston.
Which works just like a car engine.
A very similar concept, yeah. You have a solid metal cylinder and a solid metal piston sliding inside it, sealed with O-rings. And because it's metal on metal, well, lubricated metal, you can use much higher air pressure.
Oh, I see.
A diaphragm might burst at 50 or 60 psi. A piston can handle significantly more, which gives you way more thrust for those big, stubborn valves.
Okay, so we have the mechanism, air pushes stuff. But this brings us to what I think is the most critical concept in this entire document.
The idea of fail-safe.
Exactly, fail-safe.
This is the golden rule of industrial design. You don't design for the best-case scenario.
You design for the apocalypse.
You design for the apocalypse. You design for when the power grid fails and the air compressor shuts down.
The notes use these terms direct acting and reverse acting. And at first glance, I thought, okay, this is just boring technical jargon. But then you realize this is actually a logic puzzle about safety.
It is. Let's decode it. Direct acting usually means air to extend. You add air, the stem goes down.
Okay.
Reverse acting is air to retract. You add air, the stem comes up. But the air is only half the story. The real hero is the spring.
The spring that opposes the air.
Precisely.
Yeah.
Most pneumatic actuators are single-acting. Air pushes one way, a massive steel spring pushes the other way. So the question every engineer has to ask is, if the air compressor dies, or the power goes out, and the air pressure drops to zero, what does the spring do?
And that depends entirely on what is flowing through the pipe.
Correct. Let's play a game. You're designing a nuclear power plant. You have a valve controlling the cooling water flowing into the reactor core.
Okay. High stakes.
If the power fails, do you want that valve to close?
Absolutely not. If it closes, the cooling stops, the core overheats, and we have a meltdown. I need that water flowing no matter what.
Right, so you select a fail-open actuator, you rig it so the spring pushes the valve open. During normal operation, you use air pressure to compress that spring and hold the valve closed or modulated.
But the moment the air dies...
The spring takes over, snaps the valve open, and floods the core with water. The system saves itself.
Wow.
Now, swap scenarios. You have a valve controlling high-pressure steam going into a turbine. If you lose control, you don't want that steam just blasting in uncontrolled.
Right, you'd overspeed the turbine, maybe throw a blade or blow a seal, so you want fail close.
Exactly. You use the air to hold the valve open against the spring. If the air cuts out, the spring slams the valve shut.
It's amazing because it's a decision made by physics. It's not code, it's not an algorithm.
It's just stored mechanical energy.
Just waiting for the air to get out of the way.
And that reliability is why pneumatics are still the standard. A spring doesn't need a software update. But air isn't the only option.
No.
The source material spends some time on electric and hydraulic actuators, specifically for when air just doesn't cut it.
Let's talk about the electric ones. The text distinguishes between solenoids and motors. A solenoid is basically a magnet, right?
It's an electromagnet. You run current through a coil, it creates a magnetic field, and that field sucks a metal plunger upwards. It's very fast, but it's binary.
Binary.
It's either fully open or fully closed.
So you wouldn't use a solenoid to throttle a valve to, say, exactly 50%?
No. For that, you use a motor, a stepper motor or a servo. They are incredibly precise. They can position a valve to within a fraction of a millimeter.
But the downside is cost.
Cost, complexity, and failure modes.
Mm.
If the power goes out on an electric motor, it usually just stays exactly where it was. It's called fail last position.
Which could be good or bad.
It could be fine for some things, but really dangerous for others. To make it fail safe, you need backup batteries or giant capacitors, which just adds more maintenance.
Okay, now for the heavyweights. The electrohydraulic actuators. The notes call these the powerhouse.
And they are. If you need to close a massive pipeline valve against 1,000 psi of pressure, you need to do it in 1 second, you use hydraulics.
What gives hydraulic fluid the edge over air?
Compressibility. Or the lack of it. This is a fundamental physics nugget. Imagine you have a syringe full of air. You put your finger over the tip and push the plunger. What happens?
The air squishes, the plunger goes down a bit, but the air just compresses. It's spongy.
Exactly. There is a lag. The energy is absorbed by the gas before it does work. Now, imagine that syringe is full of water or oil. You push the plunger, and if the tip is blocked, the plunger doesn't move at all. Liquid is effectively incompressible.
So when the hydraulic pump pushes, the force is transferred instantly.
Instantly and with zero loss. Pneumatic systems typically run at maybe 80 to 100 psi because compressing air to high pressures is energy intensive and dangerous. Hydraulic systems and actuators can run at 2,000 or 3,000 psi.
Wow.
A completely different weight class. It's like comparing a bicycle pump to a hydraulic press.
But with great power comes great complexity.
And mess. You need pumps, reservoirs, filters, and if it leaks, you have an environmental hazard. That's why you save them for the really big jobs where nothing else will work.
Okay, so we've covered the power sources, air, electric, fluid, but not all valves move up and down. A lot of industrial valves are ball valves or butterfly valves. They turn.
Quarter turn valves, that's right.
The source has some diagrams here for rotary actuators, and I have to say the engineering is pretty clever.
Yeah.
The first one is rack and pinion. I feel like I've heard that term in car steering.
It's the same principle.
Yeah.
Imagine a flat bar with gear teeth cut into it. That's the rack. And a round gear, the pinion. If you push the rack in a straight line, it forces the pinion to rotate.
So in the actuator, the air pushes a piston, the piston pushes the rack, and the rack spins the gear attached to the valve stem.
Exactly. And usually they use a dual rack design. You have two pistons pushing racks on opposite sides of the gear. It doubles the torque and balances the forces on the stem so it doesn't bend. It's simple and very effective.
Then there is the Scotch yoke, which I maintain sounds like a pub order.
Well, that was Scotch yoke, neat. No, it's a mechanism for converting linear motion to rotary, but it has a specific superpower.
Oh,
The geometry of the yoke, it's like a sliding pin in a slot, generates a torque curve that is U-shaped. It gives you massive torque at the very beginning and the very end of the stroke, and less in the middle.
why is that important? Why do you need more force at the start and end?
Think about opening a jar of pickles. What's the hardest part?
That initial pop, breaking the seal.
Exactly. Valves are the same. When a valve has been closed for a week, the seal is tight. Breaking it off the seat requires huge force. Once it's turning, it's easy.
And then closing it again.
Then when you close it, you need huge force again to squash the seal tight. The Scotch yoke delivers that force exactly where you need it, at the breakout and the reseat, and less in the middle where it's just traveling.
That is really smart mechanical design. It's tailored to the problem.
It is. But all of this muscle piston, rack, yoke, it's all dumb. It just pushes. It needs a brain to tell it how much to push.
And that leads us to the accessories section. The valve positioner seems to be the critical component here.
The positioner is the interface between the digital control room and the analog valve. It operates on a principle called negative feedback.
Let's unpack that. Negative feedback.
Okay, so the control room sends a signal. Open to 50%. The actuator pushes the valve. But how does the control room know it's actually at 50%?
Right. There could be friction, or the wind's blowing. Maybe the stem is rusty.
Anything.
Yeah.
The actuator might think it's at 50%, but it's only at 40%. The positioner has a mechanical arm, or a sensor, that is physically attached to the valve stem. It looks at the actual position. It says, hey, the boss wanted 50%, but you're only at 40%. I'm going to pump more air in until you get there.
So it's actively correcting the error.
Constantly. It's constantly fighting to keep the reality aligned with the command. Without a positioner, you're just guessing. With it, you have precision.
And then there are volume boosters. The text compares them to a turbocharger.
That's a good analogy. Sometimes the signal from the positioner is accurate, but it's low volume. It's a whisper. But if you have a giant valve, you need a shout. You need a lot of air fast to fill that cylinder.
I see.
The volume booster takes that quiet pilot signal and dumps a massive volume of air from the supply line into the actuator to stroke the valve fast.
And finally, the IP transducer.
Current of pressure. This is the translator. The control room computer speaks electricity, usually a 4 to 20 milliamp signal. The valve speaks air pressure, usually 3 to 15 psig.
So the IP transducer is the go-between.
It takes the electrical command and converts it into the pneumatic pressure the valve understands.
So we've got the parts. We've got the muscle, the brain, the translator. Now we get to the part of the source material that I found the most difficult, but also the most impressive.
The bench set.
The bench set.
This is the core skill of an instrument technician. This is what separates the pros from the amateurs.
The name implies you're setting it up on a workbench, not out in the field.
Right. You're in the shop. It's quiet. There's no pressure in the pipes yet. You are calibrating the spring.
And that's the problem, isn't it? Because when you install that valve in the field, there will be pressure in the pipe. And the text talks about flow force.
This is the variable that trips people up. Imagine you have a valve plug. It's basically a cork. And you are trying to push that cork down to stop the flow. But the flow, let's say it's high pressure water, is pushing up against that cork with 500 pounds of force.
So the fluid is fighting the actuator.
It is. It's helping to push the valve open. This is called the unbalanced force.
Okay, so let's look at the math. The formula in the text is simply force, pressure, area.
It sounds simple, but let's apply it. Say you have a valve plug with an area of 2 square inches, and the pressure in the pipe is 100 psi.
So 100 times 2 is 200 pounds of force pushing up?
200 pounds.
Yeah.
And it is when you consider the spring, that means your actuator spring needs to push down with 200 pounds of force just to touch the seat.
And it's before you even start creating a seal.
Right. You are fighting a ghost force that doesn't exist yet while you're standing there on the bench.
So if I calibrate the spring on the bench to be perfect without accounting for that ghost force when I bolt it into the pipe,
It will leak. The spring won't be strong enough to hold the valve shut against the water pressure. The valve will just float open.
so what do?
You cheat. Well, you calculate. You preload the spring. You tighten the spring adjuster on the bench, compressing it down so it's already pushing with that extra 200 pounds of force.
The text calls this the bench range versus the field range.
Correct. The control room might send a signal corresponding to standard pressures, like 3 to 15 psi. But on the bench, you might set the spring to start moving at 8 psi instead of 3. You are intentionally miscalibrating it relative to the air to compensate for the fluid force it will encounter later.
You're programming the spring with a wrench.
That's a great way to put it. And if you get the math wrong, the valve leaks, the process becomes unstable, or you can't shut down in an emergency. It's high-stakes algebra. You have
Wow.
to trust your calculation because you can't simulate that pipe pressure in the shop easily.
Speaking of high stakes, we have to talk about the final section of this module, the hazards. I think we tend to look at a valve and think it's just a lump of metal, but this document treats them like unexploded ordnance.
That is the appropriate mindset. These devices store energy, massive amounts of it.
The first hazard is the spring itself.
Think about what we just discussed. We are compressing a heavy steel spring with hundreds or thousands of pounds of force. That is stored energy. If you decide to take that actuator apart for maintenance, and you undo the casing bolts without relieving that spring tension first,
The casing becomes a projectile.
it can blow the top off and go right through a concrete wall, or right through you. I've heard horror stories.
I can imagine.
The training emphasizes checking the spring adjuster and backing it off completely until the spring is loose. You never, ever touch a casing bolt until you are certain the spring is dead.
And then there's the fluid, the hydraulic hazard. This one actually gave me chills. High pressure injection.
This is a silent killer. We think of a leak as a drip, but at 2000 psi, a leak through a pinhole isn't a drip, it's a laser beam of fluid. It's so fine and so fast you might not even see it.
But if you run your hand over it,
It acts like a hypodermic needle. It pierces the skin instantly and injects hydraulic fluid deep into your tissue.
and the text says it might not even hurt that much at first.
That's the danger. It feels like a bee sting or a wire prick. You might ignore it. But the fluid is toxic. It starts destroying the tissue from the inside out. Within hours, your hand is swelling up.
Oh man.
If you don't get surgery immediately to clean it out, you're looking at gangrene and amputation.
The rule is never use your hand to check for a leak.
Never. Use a piece of cardboard or wood. You wave a piece of cardboard over the line. If the cardboard gets cut or wet, you know you have a leak. But never your hand.
And on top of the physical trauma, the fluids themselves are nasty. The source mentions carcinogens like lead naphthenate.
Yeah, I saw that. It's an additive used in some older lubricants to help them handle high pressure.
And it sounds terrifying.
It is. It's banned in many places now, like Canada, but the text warns that it can still be found in offshore equipment or old stock sitting in a warehouse and is easily absorbed through the skin.
So you're dealing with high pressure, explosive force, and toxic chemistry.
All at once.
It really changes how you look at the job of an instrument technician. It's not just turning screwdrivers, it's risk management.
It is. They are the ones walking up to these loaded cannons and making sure they work so the rest of us can have electricity and fuel. They have to respect the physics, or the physics will bite back.
So looking back at all of this, from the simple lung of the diaphragm to the complexities of the bench stat calculations, what is the big takeaway for you?
For me, it's the realization that the digital world has a physical limit. We talk so much about AI and cloud computing and automated plants. We obsess over the software.
Right.
But at the end of the day, that digital signal has to turn into a physical push.
The software has to touch the hardware.
Exactly. And that interface isn't a microchip. It's a rubber membrane, a steel spring, and a rack and pinion gear. The entire reliability of our modern infrastructure rests on these analog mechanics functioning correctly.
And specifically on that fail-safe spring.
That's the one. When the screens go black, the code stops running, and the AI goes offline, it's not the computer that saves the plant. It's a dumb, heavy spring doing exactly what physics tells it to do.
That is a powerful thought. We sleep soundly because a technician did the math to preload a spring on a workbench 5 years ago.
We certainly do.
Well, that brings us to the end of this deep dive into the muscle behind the machine. A big thank you to the technical minds at NELAIT and SEIT for the source material. It's been a real eye-opener into the hidden world of industrial control.
Always a pleasure to explore the nuts and bolts.
And for you listening, here is a final thought to chew on. Next time you turn on your faucet or watch the steam rise from a manhole cover, just remember that flow is being managed by a mechanical sentry that never sleeps, waiting for the moment it needs to snap shut and save the day. Thanks for listening, and we'll catch you on the next deep dive.